So we spent essentially 2 days on igneous rocks, and while that hurts my soul a little bit, it's going to be even worse on me to spend a short amount of time on sedimentary rocks. Sedimentary, this is the stuff I love, um, and so I will try to cram everything in, but there's going to be a lot of cramming going on. So here we are, off and running with the first bit, with what is weathering. Okay, to start things off, let's talk about weathering versus erosion. These are not the same thing. So weathering is breaking down material. So here we are. Let's say this is one of our big, because of the color, we'll say it's big olivine crystal. So weathering can be of several different forms. We can physically weather that one crystal into a bunch of smaller pieces. We could chemically change the mineral to some other mineralogy or some other chemistry even, and make sure you ask if you don't know about what the difference in that is. Uh, we can change shapes, stuff like that. Then, as opposed to erosion is moving material away. So weathering is breaking it down, erosion is moving it away. And the horrible blue drawing at the bottom is supposed to be a stream or something with some little waves on the top. But so we start actually transporting our weathered sediment or our weathered material away. So that's the difference in weathering and erosion. Now, weathering specifically, and we're not going to talk about erosion yet. That's going to be a subsequent lecture. But just our weathering. We can have our weathering in a couple of different ways. We can have chemical and or physical weathering. Just like you would have seen in a chemistry class, chemical change versus physical change. So think back to what you would see in a chemistry class. And I know not all of you have had one yet. So if you do have a chemistry class, you'll see a lot of this. So a physical change only changes the size, the shape, the physical properties involved. It does not change the chemistry at all. And as opposed to a chemical change, which does change the chemistry. So, like in chemistry class, we would talk about melting. If you melt ice, it was H2O when it was ice, and it was H2O once you melt it into liquid water. Did not change the chemistry. It's still H2O. But if you run an electrical current through it, you can change it to H2 gas and O2 gas. Totally change the chemistry. Okay, same stuff. So let's talk about, I think a couple of folks had different versions of olivine on the midterm. So the same idea, and we're going to get into what's going on with that. Physical change, you take your olivine crystal and you break it down into smaller and smaller pieces of olivine. But it was iron. It was Fe. Let's say Fe2SiO4 to start with, right? Well, if it's Fe2SiO4 to start with, and a big, huge crystal, and you break it or round it or do any of these other physical changes to it, all the little pieces, they might be small, they might be almost microscopic, but each of them is still Fe2SiO4. As opposed to chemical change, where we might change the iron in it from iron 2+ to iron 3+. We might break the silica. We could change it to, instead of that nesosilicate, we could change it to an inosilicate, pyroxene, something like that. Well, the formula is not going to be the same anymore. Even if it's got the same elements in it, if the numbers change, we've changed it chemically. Or we might pull the iron off, dissolve it in an acid, or replace the silicon with aluminum or something like that. Those are all chemical changes. They do change the chemical formula. So a major difference in the types of weathering there. Chemical versus physical. Okay, and so we're going to take physical weathering first before we tackle chemical. We're going to get into all the chemistry and the chemical. But the physical weathering first, and So we'll take each of these in series through there. I was wondering a thing. So I haven't written the quiz for this yet, so maybe I will somehow tie this in. But what do you do as a student to take notes the on these lectures or on anything else that we do? Do you? I mean, there are a couple of things we could talk about here. Do you just watch it and hope that it all goes in your head and stays? Just process it auditorily and like try to let it perk into your mind there. Do you write things out? Like if you write things out, it would just be a good slide here to just take this one, and then on each of these, kind of put you a definition as we go through slide after slide, try to figure out what they are. I've seen some other folks that make concept maps, how each of these things might relate to each other, stuff like that. I don't know. I would be interested. I'm going to ask a question somehow on the upcoming quiz for this. How do you make notes, or do you? I guess is also a valid part of that question. How do you make notes for this class and for other classes that you might be taking? I have to figure out a way to ask that too. How it's different. Oh, another thing I noticed on this. So, and I think I did it already once. Let me change this so I can circle it. So I will accidentally do this right here without thinking about it. So these are abbreviations, and I get kind of fast when I'm trying to write out all this stuff, and I start abbreviating things without realizing it. So you'll see certain ones show up again and again. XLL is crystal. That's my abbreviation for crystal. And I think I have used one before now that just said WXT. And WXT is weathering. We'll get some others in there, like MXT will be for metamorphism or metamorphosis. So stuff like that. You'll see me do these abbreviations, and if they're ever confusing to you, just remind me that I'm doing them. I'll try to at least explain them as we go. Okay, ablation is the physically breaking chunks off of your rock. So remember that we're still physically weathering here. So we're just breaking it into smaller or different shapes. Now, this one is easy to confuse with erosion. This is not the erosion part. We're not talking about moving it away. We're talking about breaking it into smaller pieces. So you can do this with wind if you think about sandblasting, the idea of sandblasting. So wind is not just air. It might carry sand particles or other things in it. You can blast these shapes. Now, this has also been eroded away, what got knocked off of this. So don't confuse that. We're talking about the breaking of it here. Whether even if all the parts that are broken off of this are just still lying around right next to it, that would be ablation. So you can also do it with glaciers. There are some neat glacier marks. I know we don't live in an area where we see them very much, but you can find where glaciers have slid across the top of rocks, and it just scratches them up. And a way to think about this with why it's important for the weathering as opposed to the erosion. I mean, it's important for both, but just for the weathering part, think about your car, right? And so as long as your paint job is in good shape, right, nice and smooth paint job, it'll resist rust really well, or it'll resist other corrosions. But once you start getting those scratches, somebody comes by and keys your car, right? That scratch, it changes the character of it. It pits it. It leaves an area for water, for acids and stuff to get to. So the actual physical change of scratching it changes the character of it so that it's more vulnerable to other things. Well, the same stuff happens with glacial erosion and weathering, because it'll scratch it, and it'll cause it to be a little more vulnerable to other stuff then. So, a little animation here for the water part. So consider this to be like a big piece of rock. It's sitting there minding its own business, right? But we've got water flowing here, right? So water's flowing. But remember that water we did on the slide a while ago, right? We put particles in it, and those particles are getting moved away by erosion, right? But while those particles are screaming along in the water, What happens when they slam into another rock that's sitting there minding its own business? Well, that slamming into breaks chunks off of the rock, and that is an act of physical weathering. Okay, so let's talk about a physical weathering of by frost. Now, the surface of our planet is typified by having water in various phases. We have gas phase, vapor phase, liquid phase, and solid with ice. Okay, so here is my liquid phase water has dripped down into this crack in a rock, but then the weather turned incredibly cold and it froze and expanded because water is one of those weird things that actually takes up more space in the solid form than it does in the liquid form. When it does that, it has a massive amount of force involved with it, and it can actually crack rock in half. So another neat thing that can happen with physical weathering is pressure relief, and we'll often call these exfoliation domes. And I guess technically an exfoliation dome has to have that dome shape to it. If you, we talked about Stone Mountain and the granite there before. If you happen to spend any time there, there's actually a cave at Stone Mountain. It's not a limestone cave though because it's granite, but it's what's called an exfoliation dome. So what's happened is you have this pluton, this granite, and remember that the granite formed because it's phaneritic. We know this. It formed deep underground, right? And because of that pressure and temperature, that's where it would be happiest. And it was under super high pressure when it formed. But then now that it's weathered away, and we'll talk about the weathering and erosion process that exposed it. But as it was exposed, now it's at the surface. It's under much less pressure than it was when it was buried deep in the earth. Well, what it does when it does that, it starts to expand out, and the outer edges of the granite will actually pop loose. And you can see how it is onion-like. You have these layers from this granite. This one's not Stone Mountain. This is too pink. But it's popped loose from the rest of the granite, making these layers. And if you do go to Stone Mountain sometime, you can see these giant layers on top that have just broken off in these slabs. And those are called exfoliation dome or pressure relief fractures. And just like with the pressure relief, you can do a very similar thing with thermal expansion and contraction. I think this is most important in like deserts and stuff where you don't have much other like chemical weathering going on. So you have a rock, and you can repeatedly increase and decrease temperatures, especially in a desert where those swings can be so extreme. You can have really warm temperatures during the day and below freezing at night. Heard about in Atlas Mountains where they were seeing over 100 degrees Fahrenheit during the day and freezing at night, day after day. So in doing that, you really, really stress your rock, and you can break it like this. Again, it looks a lot like the pressure exfoliation domes to me. This is a smaller version, of course. And salt crystal wedging or salt crystal weathering. Now, remember, we're still talking physical, so we're not talking about any chemical action of the salt. We're just talking about as the salt crystals form, they might start to form in a place where there's not really room for them. Well, as they form, just like the water crystallizing into ice, the salt crystallizing into salt crystals, it exerts a crystallization pressure, a force, and it'll wedge apart things. It'll break it, and so it's typified by these little holes. You can see the rock hammer here for scale. You get all these little holes where salt over and over again formed in the little pores and started to break pieces out. This is a really neat one in California. You can start to see where it's getting deeper and deeper, and the salt spray is getting up here and crystallizing more, and just kind of reinforcing itself. Okay, and then living organisms can get to work on things of various sorts. You can have roots doing it. You can have worm burrows, sloths. I recently read an article about some caves in Indiana, I believe, that had originally been thought of as just limestone caves, and then they were analyzing some of the scratch patterns that they found on it, and now they are thinking that these were actually dug out by the giant Pleistocene Ice Age sloths that lived there. That they would actually dig burrows in the soft limestone, and so actually forming their own sort of caves. So anything that could actually, now remember we're still talking physical. The some of this stuff, especially with roots, is going to come back up again in chemical weathering, but this is physical, so it's actually like the wedging. You see it with sidewalks all the time where roots get under it and lift it up and break it. And I cannot resist a Tolkien reference with it. Remember that the Saruman's Tower of Orthanc was invulnerable to just about everything except the trees. The Ents were able to do something about it. Okay, I talked a little bit about this with the glacier scratching idea, but the surface area effect, and we're going to do a little bit of math with this, and so I want you to try to follow along. But this figure comes from the Johnson text, and you can find it in most introductory texts. And I really, really want you to understand this surface area effect, and so I really want you to process what's going to go on here with volume of rock and how we divide that volume up. Okay, so 3 different scenarios. So in this scenario right here, so just the big cube, all right? So let's say it is 1 centimeter by 1 centimeter, and then also 1 centimeter high. Okay, so if you find the volume, 1 centimeter times 1 centimeter times 1 centimeter, you get 1 cubic centimeter. So we have 1 cubic centimeter of this rock material. All right. Now think about your surface area, and we'll talk about what that is. It's 1 centimeter by 1 centimeter times 6, because there are 6 faces, right? So 6 square centimeters, right? So we have 1 centimeter cubed, and we have 6 centimeters square surface area. Okay. All right. So far, makes a little bit of sense, I hope. Simple volume calculation. And surface area, might not have done surface area calculation before, but you can see what I'm doing. I'm just calculating this area of 1 face and then multiplying it by the number of faces. Okay? Change colors. Let's go purple. Okay, new scenario. So what I have here is I've divided I've cut it in half along each side. Okay? So each of my little cubes here is 1/2 by 1/2 by 1/2, right? Centimeters here. So volume-wise, we multiply all 3 of those together, right? And we get what? We get 1, 2 times 2 is 4 times 2 is 8, 1/8 cubic centimeter. How many do we have? 1, 2, 3, 4, 5, 6, 7, 8. Oh, okay. So they're 1/8 cubic centimeter each, and there are 8 of them. Yeah, that makes sense. We still have the same total volume of rock. We have 1 cubic centimeter worth of rock, right? Fine. Now let's think about a face. So a face, a surface area of a face, we're just going to take 2 of those measurements, 1/2 centimeter by 1/2 centimeter, and that's going to give us 1/4 square centimeter. But how many faces do we have this time? We've got, on this cube, we've got 6. We got another 6 here. 6, 6. That's 24. And then another 24 here, so 48. So 48. So I'm going to multiply this by 48 faces. And what do you get? You get 12 square centimeters. Okay, so all I have done, I've not changed the total volume of rock that we have. We still have 1 total cubic centimeter of rock. but I have essentially doubled my surface area. And the surface area is going to be so important for weathering processes. So by chopping it into smaller cubes, I have drastically increased the surface area. And if we could take that a bit further, and I'm not going to try to write this out with the mouse here because it gets really frustrating, but these are 1/8, so basically I've cut it. So I cut it originally. Go back to the purple. Originally I cut it in half, right? Cut it in half this way. Cut it in half this way. Yeah, okay. And then I gotta go this way too. All right, so that's where my 8 cubes there came from. Now we're going to take it and we're going to do that again. We're going to cut each of those in half. And a little straighter than I'm drawing it here, but mousing. So, and I think I've missed a line. There it is. So I'm chopping it up even more, right? So let's see. So I've got each of these is 1/8 now. So 1/8 times 1/8 times 1/8 would give me 1/64 of a cubic centimeter for each cube. That's volume-wise. But there are 64 cubes. So again, we still have exactly 1 cubic centimeter of rock. But now our surface area, so let's see, 1/8, sorry, 1/4, right? Yeah, 1/4. 1/4 times 1/4 will give me 1/16 of a square centimeter for each face, right? Times 6, so 6/16, right? So that is 3/8 square centimeters for each. And we have 64 times 3/8. Let's see, 32 over 16. Lots and lots of square centimeters of surface area. I should have done the math before I started the slide, sorry, but I don't want to go back and re-record over it again. So do the math on that, and you will see that we've really exponentially increased our surface area just by chopping it into smaller and smaller cubes. Okay, spheroidal weathering, which I've also called rounding off the corners here. So the real reason this occurs is deep in the chemical physics, and we don't want to go there. So we're just going to think of this as weathering forces, and the forces, I'm putting that in quotes there. That's bad terminology, but we'll go with it. So these weathering forces. Let's think about 3 spots on our rock. This blue spot is right on the front face of this rock. The green spot is up on an edge, and the purple spot is going to be all the way on the corner, right at the corner. Okay, so our weathering forces, they come from all different directions. What direction can they hit the blue spot from? Only from out here in front. So weathering forces that are impacting this rock from out in front can hit the blue spot. That's it. The green one, however, the green one's up here on an edge, excuse me. So these same forces that can hit the blue spot, they can also hit the green spot. But now you can get these weathering forces coming from above can also hit the green spot. So it's kind of getting attacked from 2 directions, which is worse for it. Let's go over the purple spot. The purple spot is on a corner, so let's see. The blue one, so the forces coming in from the front like the blue one, yep, they can hit it. Forces coming in from the top, so that's the second one like the green, but now even the forces coming in from this other side can hit it. So the purple can get hit from 3 directions. So what happens is the blue spot is most protected. It's least likely to get weathered. The green one is up here on an edge, and so it goes away a little more easily, and the purple is most easily weathered. So the purple is most likely to go away first, followed by the green, and eventually you'll weather down into where the blue one is. And really, we could have a yellow spot like deep inside the rock that we can't even get to with any of the forces, so it's still there. Your result is a nice spheroidal or rounded. And technically those mean different things, but we won't worry about it here. So this rounded or spheroidal system where the corners are rounded off. You see this a lot in like stream gravels and stuff. You can break them, and sometimes they get broken naturally, but most of them are going to be in a nice rounded form like that. Chemical weathering. So all that previous was all supposed to be physical weathering. Now we're going to talk about chemical weathering. So chemical weathering could be of a lot of different types: dissolution, acid attack, oxidation, hydrolysis. We're going to go through each of those, but there are plenty of other examples. One that I just thought of as I started recording that I should have put on here was phase change. Those phase diagrams that you've probably come to love so much now. Phase changes are so important in mineralogy and in geology in general. I won't go back to them yet. Just remember that that's another process that could be. There are a lot of other ones. We'll definitely return to phase diagrams when we get to metamorphics. So I will give you a break on them for now. And we'll just talk about these 4 different types as examples of chemical weathering. So as the simplest of these, let's talk about dissolution. So this is just stuff dissolving. I've drawn I didn't draw it, I stole it, but a generic crystal here. And this could be like your sodium chloride. The pluses would be the sodium in that case, and the green negatives would be your chlorides. So I'm just going to look at this green and white crystal as if it is the sodium chloride for an example, okay? So we're going to put water in. So these red and whites are our water molecules, the big oxygen with the 2 little lobed protons or hydrogens sticking off of it. So that's H2O. All right, so what's happening here? Now, Ben, I know that you will have seen more chemistry and talk about how my chemical equation is vastly, vastly simplified here. We should talk about hydration spheres on these ions and stuff. But at the simple level, what's happening is you're surrounding your chloride ion with some of these polar water molecules. So see how that hydrogen end of that little water molecule is sticking towards the negative. This one is, and this one is, and they're starting to surround it and neutralize some of that charge. Same thing over here, but they're using the oxygen end, which is the negative end. So what's happening is the water molecules are starting to surround and take away these ionic bits from the crystal, and they're dissolving it. Now, I use sodium chloride here because I think it should be intuitive to you here. If you take a big block of sodium chloride, rock salt, and you drop it in a bucket of water, what's going to happen to it? It's going to start to dissolve. And this is a cartoon picture of what's going on down at the molecular level when that sodium chloride is dissolving like that. Your water molecules, your solvent molecules, which in this case are water, are starting to surround and coat your individual ions from your crystal and take them away into solution. That's dissolution. And of course, you saw acid attack back when we were testing minerals, and one of the cleanest ones to identify. You can be fairly sure, at least from the set of minerals that we give you in this introductory type course. Well, put acid on it, and it fizz, so it's calcite. Now, in reality, there are other minerals that do that. We just kind of keep it simple for you here, but here's the chemical equation for what's going on with that. So here's our HCl, and the AQ here just means it's aqueous. It is in an aqueous solution. So that bottle that I use is not pure HCl, which I don't like messing with 14 molar HCl, but it's in water. So that the acid is dissolved. Well, when you put it on here, it's attacking. So this right here is my solid calcium carbonate. Yes, for solid. And that's my aqueous acid. And so this H part on the HCl, that H being able to come off, that's what makes it an acid, is that available proton, or H. And so what happens is this will dissolve H plus and Cl minus into solution, and the H will attack this calcium carbonate structure, putting the Ca, the calcium, into solution. and the Cl is still in solution from the acid. But now the H went and got in the calcium's place on the CO3, and you have some charge balance stuff going on with this, so that you keep it. Now, what's going on with the bubbles? What's the fizz? Well, I didn't write it, but what happens is this HCO3, that is the bicarbonate ion, so that'll actually combine under the acidic conditions where we put the hydrochloric acid on there. It'll combine with another free proton to make H2CO3, and then H2CO3 will break down into H2O and CO2. So that CO2 then comes off as CO2 gas bubbles. So that's what's happening chemically in that whole dropping acid on the calcite test. And I didn't think to mention on that last slide on the acid attack, remember that you do not have to try to memorize these formulas. All of this is where you should be able to just go back and reference it. What's important to me is not you trying to memorize any of these chemical equations or something like that. It is important to me, however, that you be able to figure out from it what's going on, to be able to look at it and say, what's happening in that chemical equation. So if that's not coming through, please let me know so that we can talk it through, make sure. I know everybody's had different amounts of chemistry. I keep saying that, but just let me know what you need in order to feel comfortable with. I'm not going to make you balance chemical equations or anything like that, so you won't have to do that. Just have to be able to talk about them. I think maybe now you understand where I'm going a little more after that midterm. Of course, I have not written the final exam yet, but it'll look something similar to that. Okay, well, on to oxidation. So oxidation is a special kind of reaction. So remember when we were talking before about some of these, maybe lecture 2? I don't remember exactly, but when we were talking about the different groups on the periodic table and how you can be sure that the halogens, the fluorine, chlorine, bromine, iodine, you can be sure that those are going to take a -1 charge. And the alkali metals, the lithium, sodium, potassium, rubidium, those you can be absolutely sure they're going to take a +1 charge. But I cautioned you that the stuff kind of in the middle, and we call it the transition elements, I cautioned you that they can do a lot of different things. And this is where that becomes important. Oxidation is changing the oxidation state, or the ion value, the ion charge value, for an ion. So in the case of iron, you can have iron 2+, or you can have iron 3+. Those are sometimes called ferrous for iron 2+, and ferric for iron 3+. So there are different versions of iron. So and there's also zero valent. We won't talk about that very much, but that's what's happening when you have unrusted or uncorroded iron. You have 2+, 0+. You have zero valent iron. So the same sort of thing can happen in chromium. If you look where it is on the periodic table, it's 2 away from iron, but it's still in that transition elements area. So anything down there kind of in the middle part of the table where they stretch it out, those can have multiple different oxidation states. And so here's a picture of our nesosilicate. Let's see, so we're some sort of olivine here with magnesium and iron involved. And so let's think about the irons, those red ones. So we balance those -4 silica tetrahedrons using 2+ or divalent iron, right? But what happens if we change that oxidation state to 3+? Well, a couple of things are going to happen with it. One, it's going to get bigger. I'm sorry, said that the wrong direction. Higher charge, so it's going to get smaller. So that iron 3+ now, I'm trying to draw a smaller circle there, is going to be smaller, right, than the iron 2+ was. Well, what's that going to do to my crystal structure? It's not going to fit anymore. It's going to be too small. It's going to rattle around in the crystal structure. So that's not good. Rattling around in a crystal structure is not good. Also, if you think about our charge balance, we needed 2 of these 2 pluses to balance that 4 minus. That was happy. But now we've got a 2 plus and a 3 plus. That's no longer balanced with the 4 minus. Now we have an excess of positive charge. The mineral is no longer happy. It'll start coming apart. So this process is called oxidation when you change the oxidation state of some of the elements. And then here we have the idea of hydrolysis of minerals. So pyrite, who had pyrite on the midterm? I forgot. Hannah, maybe? So pyrite here forms in these nice cubes, right? Here's your cubes, and they're in some sort of matrix. I don't know what that is. It's very yellow, so it could be a sulfur, some other sulfur minerals. I don't know, but it's in this matrix here. You've got these nice cubes. Those are pyrite crystal cubes. Okay, well that's happy. Looks nice, but water is a problem. So you have water and you have some oxygen going on. So here's our FeS2 is my pyrite mineral. And so what's happening is this water is attacking that and hydrating it. The iron then gets loose as in solution as iron 2 plus ions. And then do you see how H2O, along with some oxygens, has gotten around the sulfur? And so it has hydrated that sulfur into a sulfate. And in fact, what it has made here is sulfuric acid. H2SO4 is sulfuric acid. And you get some acid mine drainage from stuff like this. The pyrite, it goes away. And if you look at this example here, see a blocky hole? There's another one right there. Those holes are missing pyrite cubes. This happens. So I would love to find some nice cubic pyrite crystals, but I have found plenty of pyrite cube holes where the crystals are no longer there, and I've just got this ugly, gross sulfuric acid attacked rock left over after my pyrite cubes are gone. Okay, and I have to talk about soil formation here. So soils, all right, soils is a giant topic. That there, like at UGA, there is an entire, I think it's more than a major. It's not quite a school, but it's a whole department of soil sciences and how soils form and how that behave mechanically, chemically, biologically, everything else. There's a lot going on with soil. Don't just dismiss it. But anyway, so there's complex processes, but they tend to make a very similar soil profile everywhere. So you've got an organic horizon up top. Then you've got, so the organic horizon is where your dead grass, maybe even your living grass, and your root zones and stuff like that. Then what's called the A horizon, you have partially decayed material sitting on surface. Okay, now we get some chemical weathering going on. So this E horizon. So what's happening, you see how stark white that is in the soil profile. So what's happening here is it's leaching away some of the stuff there, particularly the iron. So it's leaching away the iron, and because iron is a lot of what gives us the reddish colors, that red color is pulled away from there and gone. So it leaves kind of a white stained area in it where stuff has been leached away. So if it pulled that iron away, where did it go? Well, it went downward into the B horizon where the leached iron, maybe some clay minerals and stuff like that are starting to accumulate from above. And then eventually you get to this C horizon down here, which is kind of the rock that's not completely rock anymore. So you get a development from new organic stuff into organic stuff mixed with rock bits, and then you get different new minerals and down to mostly rock bits, and then below this would be just rock. So like I said, this kind of soil profile development happens all over the places, all over the planet, different climates and everything else. But a big question that we deal with in geology sometimes is, do the same processes, do the soil formation processes look the same over time? And this gets to an entire field of geology that deals with paleosols, is what that's called. Paleosols means old soils. And it's a giant part of research. And Laura, we talked about the crossover between archaeology and geology, and paleosols is one of the big places where those two things overlap. And there's lots of, and this is important if you're looking at if you're looking at an academic career, what I'm about to add to research, I'm about to add an adjective that's very important. There's a lot of funded research into paleosols, so that's very important. Anyway, soils, you could go on about soils literally for entire PhDs. They do that. Okay, differential weathering. Differential weathering is what gives us most of the landscape, the surface of the planet that we see. All of it results, all might be a strong term, almost all of it at least, results from differential weathering. So what's happening here is not all rocks weather at the same rate. Some of them resist weathering better than others. Okay, so let's say we've got a person standing here on the surface of this planet, right? So these are layers of rock, and in Wednesday's lab, you saw some stuff about layering and how we start to talk about different ways to work with the layering. And you'll also see that we do stuff like we have intrusions, and we talked about this in the igneous rock section, how we can have intrusions come up inside. This would represent like a batholith here. So we've got this igneous intrusion inside, and then it cools and becomes a plutonic or intrusive type rock. Let's say it's a granite, because I'm leading towards Stone Mountain here is where I'm going. So let's say this intrusion got into the other rock layers that I've represented with that layer cake there, but it's still underground and we can't see it. So this guy who might be standing on the surface here, so that granite down there is not bothering him. He's just standing up here on this nice flat surface, right? But over time, you've got wind and rain and other weathering forces going on, and so that weathering tends it takes away the material, it'll erode away that landscape that he's standing on, so that the landscape goes down underneath him. So he's standing at a lower point now, right? Okay. Okay, still looks fine. More weathering takes away more of the landscape around him, and it leaves him at a lower point. And this keeps going until, well, now wait a minute. So now he's standing around starting to see a granite emerging from this, because the granite is much, much, much more resistant to weathering than whatever else he's standing on in the Atlanta area. That would probably be a metamorphic schist, and we'll talk about those with the metamorphic stuff. But so all this going on here, this is starting to stick up more, right? And the other stuff is going away. And eventually, it sticks up a lot. Now it's starting to look like Stone Mountain. Now, I have done this as if a guy was standing there watching it happen. And, of course, really this is taking millions, tens of millions, maybe hundreds of millions of years sometimes for this differential weathering process to happen. So it's not going to be like somebody's going to watch it happen. We come along and we see one really, really instantaneous snapshot in time, and we've got to try to work backwards and figure out what has happened. And differential weathering is one of our really big keys on how we think we got all of the landforms that we see around us now. And one last thing on this, the weathering is where we get a lot of our extractable resources, especially in the case of metals. You can get changes in phase chemistry so that things are easier to get to. I know that. Now this picture that is in the background here is an iron mine that I don't remember where this is at, but it's a giant one. That's like train cars on the top. But those just red oxide iron layers being mined there. This oxide iron was mined over here on Pigeon Mountain. So all that place that you mapped, that you did profiles on, I'm going to show you videos of and pictures from there where I did some sedimentary rock hunts over there for you. But Pigeon Mountain actually was mined for this same type of red iron oxide ore, limonite, and maybe some hematite available at the old Pigeon Mountain mines back at 1900 ish when they mined those. So, but weathering is what causes it to oxidize from whatever from the olivines or whatever it was in to start with, and end up as this iron oxide that is easier for us to extract. Working with silicates is a bear. You don't want to do that if you can help it. So this gives us a lot of our materials that we need for our civilization to function, especially in the case of metals. And uraniums do it too. Uranium oxides, one of our big. Uranium is another transition element. It can have different oxidation states too. So oxidation and other types of weathering give us a lot of our materials. Okay, well that's going to do us for weathering, and next time we'll move on to erosion, which make sure you remember weathering and erosion are different processes.